My name is Michael Coulombe. I'm a PhD student with Eric Domain working on algorithms and game hardness analysis. Game theory is a much broader topic that has a lot of different practical applications and things, but the sort of games that we usually focus on in our group are like video games and puzzles and board games, card games, things like that, that have a lot of sort of fun elements of them that makes it a very interesting thing to do research on. But also has a lot of really cool ties to actual like sort of complexity theory and understanding the hardness of different computational problems and algorithms related to them. Right, like if you think about a lot of real world games, like where you're playing, right, like a first-person shooter, right, over the internet or something, right, you have a lot of players, right, moving around a level, right, trying to coordinate, and right when you cut off their communication, trying to model these older games. Right, I mean, it's almost impossible for them to be able to coordinate in the game, right, without being able to sort of communicate information from one player to the other about what's going on in their part of, of the map, or things that they've learned about what the other team is doing. So when we think about adding communication, right, the sort of thing we were able to figure out was that the amount of communication sort of per time is a really important measure of something that we can link to how hard it is to determine whether you can decide whether or not they can win. When we were doing our research on the team games without communication especially, right, what we were doing was trying to show that a lot of these games are, right, undecidable to determine whether or not one team can win, right, and sort of we think about decidability or undecidability in terms of, right, whether or not a computer, right, whether there exists some algorithm that actually can give you the right answer, yes or no, right, when you sort of write down, here's what the game is defined to be, here are what the players are, right, does this team win, yes or no, right? And if there exists some algorithm, right, such that no matter what game you write down, right, whatever version of the game you write down, it's always able to give the right answer, that means it's decidable, right? This algorithm can decide, right, always give you the right answer, right? So on the flip side, when something is undecidable, right, you're showing that there's no algorithm that can actually give you the right answer all the time, right? So when we were doing these sort of simulations of the abstract game in the sort of real world games, right, we're really showing that, like, if I give you, right, some first-person shooter game, tell you like what does the map look like, where are the like buildings and walls, right, what characters is each player playing, what weapons do they have, what abilities do they have, right? You write all these sort of things down, right? You put it into a computer, right? You say, right, is there a winning strategy, right, for this team to win, right? And we showed that it's undecidable, right? So there's no algorithm that can actually always give you the right answer. And this doesn't necessarily tell you whether or not that team can actually win in practice, right? Because this is sort of just the existence of a winning strategy, right, over sort of an adversary that's sort of all-powerful and all-knowing, that can try to trick the other team to try to find any way to win, right? So a winning strategy, though, right, is a strategy that'll always let you win, no matter what the other team does, which is sort of the most powerful type of adversary that we deal with, the sort of worst-case adversary. We want to say, does there exist a winning strategy that'll always win? Right? It could also be useful, we haven't studied yet, having an algorithm that might be able to say that there's some probability that you can win. So we mainly focus on sort of this worst-case adversarial type of decision problem. Like a lot of these sort of research on games and results that we've shown about games, whether they're undecidable or maybe they're decidable, right? One thing we also study is if they are decidable, right, not all algorithms are created equal, right? Some algorithms, some problems require algorithms that take a really long time, right? And there's a lot of different games that we've been able to classify as different amounts of difficulty in terms of their computational solvability, where undecidability is like sort of the worst possible case of there being no algorithm. And a lot of this sort of game research has a lot of these cool connections to these sort of understanding of problems and algorithm hardness, and connecting the techniques that are usually used in these more abstract theoretical senses and applying them to things like games or puzzles but also using the research on games and puzzles to develop new techniques for the more abstract types of computer science that have their own connections to all sorts of different things.